Okay, so in this problem, we've got an elevator. So let's draw an elevator. And this elevator is going down a shaft. And it's in, unfortunately, it's in free fall. But there is a spring at the bottom here. And that elevator is going to land on the spring and compress it. Now, the mass of the elevator is 750 kilos. And it is 25 meters above the spring. And we know that the spring constant, K, of the spring is, let's say, 40,000 newtons. Newtons per meter. Okay? And what we'd like to figure out here is what's the, well, we've got a bunch of questions, okay? So first of all, what's the work done by gravity on the elevator? So the work done by gravity. Okay? Before it hits the spring. And also we'd like to know the B, what's the speed of the elevator? Just before it hits the spring again. And what else do we need to figure out here? And most interestingly, how much does the spring compress in order to stop the elevator? How far does the spring compress? Okay. Now, first of all, let's put our okay, I know that I drew this arrow here as a arrow for the direction, but we're going to do the free body diagram here. And we'll do it in a different color here. We're going to say that the force of gravity is that way on the elevator. Okay? So part A is really simple, really. Basically, all we say is, all right, force of gravity is equal to the work due to gravity is the force of gravity times the distance that it moves. And remember, once again, when F and D are in the same direction, your work is positive. Okay? So in this case, since we know the mass, it would just be mgd, that being the force, and all we get is 750 kilos times 9.8 newtons per kilogram multiplied by a distance of 25 meters, and we get an answer of 750 enter 9.8 times 25 times, and we get 183,750 joules. Okay? Now, Part B, how fast is the elevator going? Okay, well, for part B, we have to say, okay, the initial energy, and then this is just before it hits, by the way. Okay, so at the top here, this is, say, initial, right here. Let's do this in a different color. That's initial, and that's final. Okay, so initially, we've got, in terms of energy, we've got gravitational potential energy, and finally, let's say this is, zero. We don't have any gravitational potential energy anymore, but we do have kinetic energy. So we would say mgh, which is the gravitational potential, equals 1/2 mv squared. And of course the m's cancel out, and you can calculate the velocity simply by going 2 times gh square rooted equals v, and that's just going to be 2 times 9.8 newtons per kilogram, or meters per second squared, either way, times a distance of 25 meters. Okay, and that's going to be, let's 2 enter 9.8 times 25 times, and we're getting an answer of 490. Oops, wait, I think I forgot to take the square root of that. Just a sec, let me try that again. 2 enter 9.8 times 25 times, yeah, and then I have to take the square root, which is, okay, that's wrong. It's 22, I know that was a little high, 22.1 meters per second before it hits. So, right about at this location here, that's the velocity. Okay? Now, the last part of the question says, how far does the spring compress? This is I would say this is the best part of this question. These first two parts are quite simple. But if I kind of draw this a little bit bigger, let's draw the shaft here, and let's draw the spring again, and there it is. Now this is the spring compressed, so here is the elevator against it, okay, and this is where the spring used to be, but it's compressed now. Therefore this used to be 0 here, but you see it's squished. So the question is asking, what is this distance? And let's call it delta y. Okay. The way we do this is we say to ourselves, okay, initial energy equals final energy again. But this time, this is our initial location, and this is our final location. Okay, this being initial and this being final. What types of energy do we have initially? Well, the only type of energy that we had initially was kinetic energy. Remember, this is location 0, right? At this point it's 0, so there's no gravitational potential energy. So we've got kinetic energy initially, and that's it. No gravitational potential, and also no elastic potential, because at this point here the spring is not compressed. But you see, finally down here the spring is compressed, so we have elastic potential energy, but we also have gravitational potential energy, although this gravitational potential energy down here is going to be negative. But that we need to take that into consideration. So let's write out the equation. What does it look like? Well, our initial kinetic energy is 1/2 mv squared. Our elastic potential energy is 1/2 k. Now, instead of writing x here, I'm going to put delta y squared plus gravitational potential energy. Now, here's the weird part, is that actually this is mg, but this distance is actually a negative distance. So perhaps I shouldn't have used delta, because this already assumes that the delta is going to be negative, which would kind of, well, actually it won't change this one because it's negative squared. But so that means I can just put that here. So in fact, if I write it out, the problem with this is that it still does, this equation doesn't take into consideration that this guy's negative. So I'm going to change it slightly. I'm just going to make it a y instead of a delta y, just so that for simplicity's sake. And we know that it's going to be a negative distance, but you see what that does here is it makes this negative mgy. And so if we work out what y is, we now have an interesting equation, because we have 1/2 ky squared minus mgy minus 1/2 mv squared equals 0. Now, if you recognize this, this is a quadratic. This is a quadratic with, what's a quadratic in the form of, right? Quadratic is in the form, would be in the form of this. And so, in terms of A, that's A, that's B, and that's C. So, what are A, B, and C? A is equal to 1/2 k, which is equal to, I believe k was 40,000, wasn't it? I think so. Yes, it was 40,000. So that means we've got 20,000 here. B, I think M was 750, wasn't it? Yeah, it was. So 750 enter 9.8 times gives us 7,350, and that's going to be in newtons. Okay, but that's negative. Don't forget that. Negative right there. And C is also going to be negative 1/2 mv squared, which is 0.5 enter 750 times, and the velocity which we got was 22.1. So 22.1 squared times, and I am getting 183,000. That's negative 183,153. Well, 54.7. So it's 154. Now, And that's in joules. So what do we do now? Well, what we can do now is, if you have a calculator that can solve a quadratic, if you don't, you can solve a quadratic simply by going quadratic equation equals, I think it's negative b plus or minus the square root of divided by 2a. Now, inside the square root was it b squared minus 4ac? I think so. That was the quadratic equation. So negative e plus or minus. Now, if you happen to have, now in this case ours is a y, if you happen to have a quadratic equation solver, let me try putting mine in. Let me see how it works out. 20,000. And for B, 7,350. And oops, that was negative. 7,350 negative. And 183, 154. And now, if we, so we get two roots, y equals either negative 2.8 or positive 3.2. And the one we want is that one, okay? Because we've already taken into account that it's negative by the fact that we've said that here. So that's the problem. The answer, of course, is 3.2 meters. And that takes into account the spring and gravity. Hope you enjoyed this problem. It was a long one. See ya.